Igneous rocks form in two basic settings, as we have already covered. Molten rock or magma may crystallize within Earth's crust over a range of depths, or it may solidify at the Earth's surface as lava cools. The first kind, intrusive rocks, otherwise called plutonic rocks, are named after Pluto, as I said before, which is a god of the underworld in Roman mythology. We see intrusive rocks exposed at the surface only after they have crystallized, been uplifted, and when the overlying rock has been eroded away. Good examples of places where we can find intrusive igneous rocks are the Idaho Batholith, which is close to home, Yosemite National Park, Mount Rushmore in South Dakota, amongst many other places. The second kind, or extrusive or volcanic rocks, are named after Vulcan, which is the god of fire. We see these rocks at the surface shortly after crystallization, as they cool near or right at the surface. We may also see these at depth, but this only happens if they have been buried by overlying sediment through time. But initially they form at the surface. Good examples where we can go and see extrusive igneous rocks are in Hawaii, the Cascade Mountains, the Andes Mountains, the Aleutian Islands, craters of the Moon, among others. So igneous rocks are mainly composed of silicate minerals, as I've said in the past few slides. The 8 main elements that we have covered before make up 98% of most magmas. The remaining percentage come from minor amounts of other elements, amongst which we have manganese and titanium, and trace amounts of gold, silver, or uranium, for example. So, as a refresher from last chapter, there are 2 main groups of silicates that are formed when magmas begin to cool. One being the ferromagnesians, which in this slide are the green colored boxes. The ferromagnesians tend to be dark in color and heavier in weight due to their high iron and magnesium content. And then we also have the non-ferromagnesians, which in this slide look like I guess characterized by the yellow boxes. Non-ferromagnesians are light in color and also light in weight. Most of the ions that they have are aluminum, calcium, sodium, and potassium. All, again, in all of the ferromagnesian and non-ferromagnesian cases, bonding with the silicon oxygen tetrahedron. Or tetrahedra, I should say. The image above is kind of a summary of how the minerals groups are. You see, again, the 7 mineral groups in the blue boxes. So you have halides, native minerals, silicates, carbonates, sulfates, oxides, and sulfides. And for each of those, I put a little picture of one of the characteristic minerals. Under the silicates, then we have the 2 different types of either ferromagnesian or non-ferromagnesian silicates split up. So again, the ferromagnesium with green, and there we have olivine, pyroxenes, amphiboles, garnets, which I didn't put there, but also will make part of that, and biotite. And then on the non-ferromagnesian side, which are the yellow boxes again, we have things such as feldspars, either potassium or plagioclase feldspars. We have quartz, we have muscovite, and we have clay minerals. The non-ferromagnesian minerals, especially quartz and feldspars, are more silica-rich, SiO2-rich, than the ferromagnesians are. This has to do with various things, one being their formation, which is typically towards the later stages of magma cooling, when most of the ions have already been bonded to other things. So most of the material that is left is just silicon and oxygen. But it also has to do, and is perhaps more importantly due to the chemical structure that they have. If you remember from table 3.25 from your book, the more complex the chemical silicate structure is, the more silica-oxygen tetrahedra build with one another, hence not allowing for as many other ions to bond with the tetrahedra. So the silica abundance in non-ferromagnesian minerals is an important concept to grasp now before we move on into other igneous categories. So if it is a little hard to understand, I recommend that you either go to table 3.25 of your book and to the previous chapter's videos and listen to the part about the silicate chemical structures for additional information, or you repeat this little bit of the video that I said about the amount of silica in non-ferromagnesian minerals. Alright, so now we're going to jump in to understand the way that igneous rocks are classified. So igneous rocks are classified based on two things: the mineral composition and their texture. And we'll go through each of these with more detail later, but for now I just kind of want you to see what you will be doing in lab in order to classify an igneous rock. So based on the example that we have above, there's a certain chemical composition to every igneous rock. And this chemical composition is usually characterized by a set of mineralic arrangements. So depending on the minerals within the sample, and to a certain degree, based on the color of the rock, as color is a good way to tell which silicate minerals the rock have or the rock are made out of, we determine one of the four possible mineral compositions of igneous rocks. In the example that we have above, the mineral composition is mostly made out of pyroxenes, amphiboles, olivine, and some plagioclase feldspars. So overall, the rock is quite dark if you think about it, because amphiboles, pyroxenes, and olivines are all ferromagnesian minerals that tend to be pretty dark. However, because of the content of the plagioclase feldspars, it's not completely jet black. And because of the content of the olivine in there, it may even be a little bit greenish. So overall, the sample falls on the third darkest column, called mafic composition, and we'll go again in a little bit more detail later. The other basis for classification is texture, and we'll go through all of the possible textures in more detail as well later. But in our example, the rock that we have has a very fine grains without any bubbles or any glass or any different fragments within them. They're just very fine grains that are not visible to the naked eye. So if we combine both of those classification methods, we find that our rock is basalt. So I take my mafic column for mineral composition, and I take my very fine texture, and that gives me the specific rock that I'm looking at, which in this case is basalt. So we'll practice this in lab a lot, and we'll go in detail about the different mineral compositions and textures just a little bit further in the lecture. So don't get too scared if the process was not very clear from this example specifically. Alright, so this chart that you see on this slide is basically the chart that allows us to recognize the different mineral compositions that give us a classification for igneous rocks. So as you're seeing the chart, there are four main columns, one being felsic, one intermediate, one mafic, and one ultramafic. Those are the names of the possible mineral compositions that an igneous rock can have. And those specific columns are based on the minerals that the rock contains. So for the felsic column, as you're seeing in the image right below, that specific rock type contains quartz, feldspars, muscovite, and then in terms of dark minerals is going to contain biotite and amphiboles. The amount of dark minerals that felsic rocks typically have doesn't go above 10%, so very little of it, and the silica content of felsic rocks is about 70% or greater. So as you're seeing that, felsic rocks for the most part are going to be very light colored, so pinkish, sometimes if they have potassium feldspar, but for the most part they're just going to be a light gray or white, depending on what type of rock you have. The next column over is intermediate igneous rocks. So intermediate igneous rocks tend to be a little bit darker than felsic, because now they contain a larger amount of darker colored minerals. So intermediate rocks contain things such as quartz, feldspars, less potassium feldspar than felsic rocks by a lot. So usually you don't see any pink inside intermediate rocks, although you can. You have a tiny bit of muscovite, if any. And then now the percentage of dark colored minerals is about 25%. The silica content in them tends to be between 55 and 70%. Yeah, usually intermediate rocks, intermediate mineral composition rocks, they look like they have more dark than 25%. As humans, our human eye catches the dark colors better than the light ones. So a rock that has, say, 10% dark minerals and 90% light minerals, our human eye has a perception that it's really more like 20 to 80% or 25 to 75%. So that's also something to be aware of. And usually we bring in the field little cards that help us aid ourselves to determine the right amount of percentage for dark or light minerals. Okay, the next column over is the mafic column. Mafic colored minerals tend to be darker, or I should say mafic colored rocks tend to be darker due to the amount of ferromagnesian minerals or darker colored minerals. For mafic rocks, we have plagioclase, feldspar only, not potassium feldspar. We have pyroxenes. Oh, I'm going to correct that real fast. And this too. We have amphiboles. We have biotite. We have a little bit of olivine. And then we have the silica being between 45 and 55%, so less than felsic or intermediate. In this case, the dark colored mineral content is about 45 to 50%, so definitely darker colored rocks. They tend to be more black than white, if anything, but again, our eye catches the dark more than the light colored things, so it looks like it's darker. Lastly, we have the last column, which is the ultramafic type of igneous rocks. And in this type of rocks, we have mostly olivine and pyroxenes making up the rocks. Also a tiny bit of calcium-rich plagioclase feldspars. So for the most part, it is dark-colored minerals, about 80%, and then the silica content that we have for ultramafic rocks is between 40 and 45%. Okay, so again, here is the graph that you just saw in the previous slide. Again, remember that those are the main 4 columns to which an igneous rock can belong. An igneous rock is going to have either one of those mineral compositions within it, and that has to do with the crystallization sequence, and we'll go through that later in the chapter. But any igneous rock is going to have one of these types of mineral arrangements, perhaps a little bit more than the table shows you, or perhaps somewhere in between a felsic and an intermediate, or an intermediate and a mafic, but it's going to lie somewhere near those bounds, okay? Also, in the previous slide, I kept telling you that the silica content for each of those compositions. So I told you that the felsic had 70% or more, and so on and so forth. But I never told you why I told you about the silica composition or the silica percentage within the specific columns. Well, in truth, the silica content itself will play a large role in the magma's behavior. So the rocks that have a greater silica content are characteristic of magmas that are more viscous prior to crystallization, okay? The greater the silica content, the more viscous they are. Viscosity itself is basically the flowability of a material, so how fast will it flow? How fast will it move? So as an example of a highly viscous material, let's take cold honey, for example. When you pour cold honey onto a piece of bread, it will spread, but it will spread very, very slowly. But if, for example, you were to pour butter that is so hot that it's liquid onto your bread, once you pour it onto your bread, it will spread very, very fast. So the cold honey is much more viscous than the hot butter, which was very low viscosity.